Hello, everybody. Welcome back. Can you hear me? How is my sound quality today?
It's fine.
All right. Okay, we'll wait for another 2 minutes, and then we'll start. Today's lecture, right? I will put it on the YouTube. There is nothing confidential today, so it should not be a problem. Before we start, do you have any questions so far? Anyone? Okay. Right, we will wait for another minute or two, and then we will start. All right. Hello, everybody. Hello again. Welcome back. So today, just to repeat quickly what we did the last time. Last time we looked at the linear systems. So that means linear system identification. We looked at the model validation. We looked the mass spring example. So a simple system identification technique on the linear systems, right? We paid kind of attention more towards the parameter identification rather than the order selection, because we kind of knew what order the model should be, since we knew the order of the system. And then we looked at the recursive least squares algorithm, right? And the utilization of the RLS for the adaptive control. Now, today, what's wrong? So the last time, so the least squares, the recursive least squares and the adaptive control, I was running a little bit of time. So I did it quite quickly, and I want to do that today again. So we will just quickly go through the recursive least squares, and I want to do the adaptive control example again, because I'm pretty sure you did not get what I wanted to explain the last time. Then this is going to then conclude, this example is going to conclude the linear systems system identification, and then we are going to continue with the nonlinear systems today. We will take a look in general on the nonlinear system identification, and we're going to start, maybe, I don't know, maybe we will start with the multiple model networks today. If not, then we're going to continue tomorrow. Right, okay. Yes, this lecture will be on YouTube. Today, there is no kind of a material which should not be published. So it goes on YouTube. Right. Any questions so far? Okay. Right. Okay. So first, why are we doing the recursively squares? So if you remember the mass spring example, so what we have done, we have collected the data and we put the data into the matrices, and then some of the phi transposed phi, so the matrix of the collected data needed to be inverted in order to get to calculate the parameters of the model. Now imagine that the system is changing all the time. So that means if we need to identify, for example, the mass of the vehicle, which loses its mass due to the burning fuel. So that means we would need to constantly measure some signals, and we would constantly need to put them into some matrices and invert the matrix, which means that phi transposed phi matrix would grow with time, and it would be kind of a computational expensive to invert it every sample time. And with time, the matrix would be bigger and it would take longer. And then over time, it would get really, really big, right? And inversion wouldn't be possible anymore, and so on and so on. So the recursive least squares algorithm is the same. I mean, it is the least squares algorithm where we find the matrix inverse without the actual inverse. We kind of get some sort of approximation of the inverse, which is actually isn't, but it is computational less expensive. And then it can be performed usually online. And as soon as the new data point arrives, we can recalculate the parameters of the model parameters. So I have shown you the last time the derivation. It is here. It is given to you if you want to take a look at it. But I don't at this point. I don't want to go through the derivation. And what is an important at the end, right, is that the matrix P. So just a second. The matrix P. It's called, in this case, it's called the covariance matrix. The matrix P is the one that we want to kind of update, right? And the update rule is written here. So that means it's the matrix P, what it was a previous sample, minus some actually some other term, which actually involves the previous matrix P and the new data point. You see, this is hidden in this kind of a product here. And then once we calculate the matrix P for a new data point that it has just arrived, then we can calculate the new updated parameter vector theta. So then this can be then summarized as that the new prediction. So that means the new data set, the new data vector can be calculated based on the old data set plus some correction factor, right? Multiplied by the old measurements and predicted measurements based on the old parameters. So now here is some correction factor, and we're talking about the lambda. So in the calculation of the covariance matrix P, we see some lambda. And this lambda is so-called a forgetting factor. Have you ever heard for a forgetting factor before? Right, so basically this forgetting factor, this lambda tells us how important for the new prediction or for the new parameter calculations are the old values. So that means if the forgetting factor lambda is high, is 1, right? That means that all past measurements are going to be taken into account in order to calculate the new model parameters. If lambda is small, is lower, right? It's a value between, I don't know, let's say 0.8. So that means more weight it is going to be put on the kind of a latest measurements than to the old ones. And now this is important if our system changes fast, changes quickly. So imagine that the mass of the vehicle changes relatively quickly. So that means if you want to update and if you want to get the correct model parameters, then the lambda should be smaller, should be lower. And if it doesn't, then the lambda should be bigger. So the choice of the forgetting factor is depends of how fast our updates needs to be done, right? And this is the designer parameters. That means it's up to you to select it correctly. We might take a look at this in the example. Do you have any questions so far? Have any of you used the least squares, recursive least squares before? No. Okay. Right. So basically, that means that using the recursive least squares, it means the new measurements are coming in, and for each new measurement, the new parameter vector can be updated. This in reality, this is cool. This is very good. So that means that the model can be constantly adapted, right? Now the actual algorithm would look something like that. So when we have our system, right, and we measure input and output data, input and output signal. So of course it needs to be sampled and then and filtered and everything, right? So what we do then with using the recursive least squares algorithm, the parameters of the model are constantly updated, right? So based on the new measurements, based on the old measurements, the model gets constantly updated. This can be applied for adaptive control, right? It can be applied for self-tuning controllers, right? And for the, let's say, for the systems when the operating point changes and when the system changes with the operating point. This is going to be much clearer now with the example. And this example, we're going to use the adaptive control. So we have a nonlinear system here, right? So you're right. Someone someone pointed it out, right, the last time, that with the in the linear system section, right, we are dealing with the nonlinear systems. This is correct, right? But it'll be much clearer why are we doing that when we get through this example. So what for this particular example means, right, that I'll go to this one. So we have a chemical reactor, which means that the property of the reactor changes with the operating point, right? So that means if we tune a controller for one operating point, right, it will work at that particular operating point. And then when the operating point changes, the dynamic of the system changes. So that means the controller needs to change together with it. If not, then the parameters for a controller would not be suitable for this new operating point anymore. And system would not, the quality of control would decrease. And in the worst case, system would go unstable. So what do we use? What do we do then, right? We have our system which changes over time with the operating point. We apply the recursive least squares estimator, which constantly is monitoring and it is constantly updating the model parameters. When the model parameters change, the recursive least square estimator will provide the new model parameters. And now, based on the model parameters, so basically based on the model, we have some tuning algorithm. So in this case, this is called a pole placement tuning algorithm. And it is based in the way so that the controller parameters can be calculated when we have a model parameters. So this is done, this is shown here. Once we have once we estimate the A's and B's of the model, it is easy to calculate immediately. We just do some multiplication, and then we get the parameters of the controller, which is decomposed into the two kind of branches. One is the feed forward branch and one is the feedback part, right? And S, R, and T are polynomials, right? They are calculated directly from the model parameters, assuming that we know what the closed loop behavior of the overall system should be. Now, is this clear what I have just said? Ask questions now if you do not understand what I'm talking about. This is important for the understanding of the example. Is this clear? Right. So we have a system which changes with over time. Somehow we constantly update, we constantly identifying the system online based on the model, which is constantly updated. We constantly update the controller parameters. So that's the point. So our system that we want to control and then kind of constantly identify is a continuous state tank reactor, CSTR in short. So this is the chemical process, and the differential. So the input to the system is the temperature, the mass flow rate of the coolant, and actually the coolant cools down the chemical reactor, right? And when the chemical reaction is actually taking place, it releases heat, and this heat needs to be taken away by the coolant. right? And the input to our system is mass flow rate of the coolant, and the output of our system is the concentration of the product, right? And the product depends heavily on the temperature of the reaction. So that means that with the coolant flow rate, right, the temperature of the reaction is controlled, is kept steady, right? And in this way, the product concentration is controlled as well. So the differential equations shown here, right, they kind of characterize the system. And we see this system is very nonlinear. Someone should tell me now, I made a statement now, this system is nonlinear. How do we know that? Well, so someone should tell me, right, how do we know that this system is nonlinear and that it is heavy nonlinear? Come on.
The exponents, the exponential function.
Yes. So we have, so if the system was linear, then there would be some numbers. So that means some letters, A, B, C, or something, right? Which they would be just multiplied, right? And some of them together, so linear combination. But here we have just about everything, the exponentials, so lots of different things. So this shows us that the system is heavily nonlinear. And now we will examine, right, the how nonlinear. Okay, so now I am going to run the examples that we have started the other day, so the last week. And I will go through that a little bit slower. So I'm just starting it right now. How do you, now the Simulink block diagram, it is going to appear. So tell me, I mean, how well do you see the block diagram? So if I show you now this block diagram, can you see different blocks?
Yes, it's fine.
Okay. So first I'm going to explain a little bit what we are doing here. So this is our model. No, this is our plant, right? This is where we measure the input and output signals, right? And the plant, the model of the plant is two differential equations, as I have showed before here. So basically those two differential equations are implemented in Simulink, right? So now we pretend that we don't know what is in this plant. I mean, we are just able to look on the input and the output signals. So we have the output signal, and we have something that goes into the plant, right? We have the integrator here. This is the kind of something that removes the steady state error. So this is the additional to the controller, or let me put it this way, that the controller is separated, is decomposed in the way that it has the integrator on its own. So that means input to the recursive least squares estimator and the output of the plant, and then the recursive least squares provide us the parameters of the model, right? So which are here, and we will observe them as well, right? And now these parameters of the model, right? So that means we have the parameters of the model, then they get calculated. So from the model, the controller is calculated using this set of equations. So this set of equation here is implemented in this controller tuning box. And then this controller tuning box, the parameters are then kind of transferred to the feedback and feed-forward part of the controller, right? And just for comparison, right, we have a model which is constantly identified in parallel. So we wouldn't need that for the control strategy, but it is just to observe what our model is doing. Okay. Now, if you remember the where is it now? If you remember this one. This is the matrix P, right? So, and this is the matrix, depends which size depends of the order of the model. In this case, we have the model which has a second order. So that means we have, I don't know, 4 by 4 parameters, I guess. It is sometimes it's very useful to take a look what kind of how this matrix looks like, right? And this is our P matrix display, right? Which tells us the numbers. Yes, it is 1, 2, 3, 4 by 4 matrix. So now this matrix needs to be well conditioned, right? So it is, we are not looking for the inverse, but it's still for the good parameter estimation, it needs to be well conditioned, right? And there is a display when I'm going to run it, right? We're going to take a look into the P matrix display, which is kind of a color coded. So the black squares means the high numbers, and the white ones mean the low number, right? So, and what we want to see on diagonal kind of a evenly distributed matrix. What else is important? The important thing is, if you remember last week, we said that it is very, very important to have a good excitation signal in order to get the good parameter estimates. So our excitation signal is added, is a Prbs signal, right? Which we also looked, and it is added at the input to the plant, right? So this one is constantly exciting the system with the small amplitudes, and then based on the response of the excitation, we are able to estimate the parameters. Okay, questions so far? No. Right, I'm going to run it now. Okay, so here I have a control panel, as I said, right? So in which I am kind of running the simulation. So first, I am going to run the system for a while in open loop. So that means that I get a little bit of time to the estimator in order to estimate the parameters, in order that the controller gets tuned automatically. And then after a while, I am going to turn kind of close the loop. So that means that the controller gets into the loop. Here I have a set point change, and here I can turn on and off the estimator, so the update. Okay, let's run it. As I said before last week, right? On a good day, this is a kind of it is likely that things go wrong, right? On a bad day, it doesn't even work. but this is something I want you to realize, something that you want you to see. Okay, one. Now, this is a P matrix display, right? So these are the parameters. These are the elements. Those squares, they represent the elements in the matrix, right? And when we get the pattern, when we get on the diagonal, let's say this kind of a pattern is okay, right? So big numbers and the small numbers, right, in the matrix and in some sort of a diagonal, right? That's okay. So that means that the matrix, that the P matrix is well conditioned. Right. Now let's take a look on our scope. So on this side, these are the parameters that we identify. So theta 1, theta 2, theta 3, theta 4. So there are four parameters that they need to be identified, estimated. This is a PRBS signal. So that means the signal that it is injected into the system, right, in order to excite the system with the low amplitudes, low magnitudes. This is the this is the output of the model, right? So the output of this model that we're looking at, and this is the set point and the planned output. So now I zoomed it in. So you see here the scale is very small. So, and what we see here is how our plant is reacting on the PRBS excitation. You see this, right? And now we are still running the system in the open loop, right? And since the matrix is now well conditioned, so that means that the parameters are well estimated. So you see they went from some values and then they went to the others, and now they're constant, they're kind of a steady. They're not constant, but they're steady. So now it is safe to switch the controller into the loop because it has been tuned well, right? Now I'm going to turn the controller in. Okay, and now what we see the output of the plant is actually now following with the set point, and basically the excitation, the response on the excitation is smaller. Okay, so now what I could do now, I could see what is my, so now what we have the constant controller tuning. So now what you see now is the auto tuning. So the controller tunes itself. So now we are happy at this particular point, and I can turn the recursively squares out estimator off and the controller tuning off. So now we have the controller with the fixed parameters, and it's not updating anymore, right? And now what I'm going to do, I'm going to do a set point change. This point, for example, like that. Like this, right? And then I'm going to put it back to like this. All right. Is this clear what I have done up until now?
Yes.
Right. Okay, now what I'm going to do now, I am going to change the set point, right, to a different value, right, like this. So now our system, so our concentration is asked to be something different, right? Right, and I'm going to move it up to somewhere here, right? And at this operating point, the system behaves differently. than at the low operating point. The dynamic of this system is different. And we're going to see that when we do the step, right, the step test on the higher operating point, like this. And now we're going to put it back down where it was before. It is hard to see now because of the zoom, or maybe I will do that as well. So what you see here is that the system behaves here differently. It has some level of the oscillations. And what I'm going to do now, right, I'm going to turn the recursive, so the adaptation again. So the self-tuning, so the controller is going to get self-tuned again, right, at this operating point. You see, now the P matrix got different, and now when this, let's say, square is going to go back to the white, right? So then that means it's a diagonal again, which means at this point, now we have a new model parameters estimated, and hence a new controller parameters. And you see here is it's doing something which it shouldn't. And now you see at this point, right, the model output, right? Okay, now at this high operating point, the controller has been retuned. It has a new controller parameters. So I'm going to turn it off again. And I'm going to do the set point change again, right? So like this. And then back, right? Like this. Right? And now what I'm going to do again, I'm going to bring system down to the low operating point, right, without the adaptation. Something like that. And now at this operating point, I'm going to do again the step test with the parameters that they have been identified at the high operating point, like this. Okay, and now I'm going to stop simulation and we're going to observe the results. Okay, so this is now my plot of the set point and the planned output. These are the parameters, and this is the model output. So first, we have done our controller tuning in this region here. Then we stopped the controller tuning and we did the step test on the low operating point. Right? And now, since controller is really nicely well tuned, we get the response with a little bit overshoot. This response, it has been defined in advance. So we would like to have that kind of a response, right? And now our automatic controller tuning provides us with the controller which provides the closed loop response as we want it, right? Like this. We're happy with that here. Now, then the adaptation was turned off and we moved the system at the higher operating point, and we did the step test again. And what do we see? We see with the parameters that when the system, when the controller was identified at the lower operating point, right, the response is different. It oscillates more, right? It oscillates more and it has a higher overshoot. right? And this is not the response that we want. So what we do, we repeat the controller tuning again here, and then we stop the controller tuning and we take a look at the parameter, at the response again. And again, we see now that after the controller has been retuned, we get the response which is the way that we want to have it. And then again, if we take a look what happens at the lower operating point, right, with what happens with the system at the low operating point using the parameters it being identified at the high operating point, we see again that the system, if you did the analysis, you would see that the system is much slower, right? It takes longer for the closed loop to settle, right? So that means, is this clear? Okay, wait. And for this, you do already the Prbs over the set point. Yeah. Over the set point.
Yes, it's
correct.
clear.
Go on. Did someone wanted to ask something?
No, I just said it's clear.
Yeah, okay, it's clear. All right, so now this is the adaptive control, right? So you see that the system, that basically now what I have demonstrated is the automatic tuning of the controller. We can quickly take a look of what happens with the model output, right? We see that the model, right, the model, so that means the model identified at the different operating points, it has a different response, right? So that means that the model at the particular operating point is different. Okay, so Philip and Dennis, you're asking about where the PRBS is injected into the system. Is this what you're asking? Okay, let's take a look. So, look, here is the PRBS. It is injected. Either it could be at the set point, but in this case, it isn't. The PRBS is injected, right? In front of the system, in front of the plant, right? So the input to the recursive least square estimator is here, right? And the PRBS has been injected in front of it. Is this clear now? All right. So, but it is important, right? Without injecting the PRBS, we wouldn't be able to identify any parameters. How big the PRBS needs to be? Okay, now this is extremely important and an extremely good question. No, there is no rule of thumb how big the PRBS should be, right? But the point is, when you grow up and when you become the control engineers, right, you will want to inject the PRBS or any test signal into the plant in order to identify the models. And you will talk to the plant manager or the whoever, right? And they will go mad. They will not let you inject anything into the system because they are afraid that you're going to break something. And then you will beg them and beg them again and again, and then somehow they will let you do it, right? But they will tell you that your system that you want to inject should not disturb the process. So that means that PRBS should be as small as possible. But again, it should be big enough in order to excite the system enough that you're able to identify the parameters, right? So it should be, from your side, from the identification point of view, the PRBS should be as big as possible, right? But from the let's say a process point of view, the signal should be as small as possible in order not to disturb the plant. And if we take a look, here, right? Maybe, so we'll see how much, you see, if we really zoom it in, we see how actually no, it's here, how the PRBS really disturbs the output of the plant. It does disturb it, right? But very little, but still enough in order to get the parameters, right? And here you see how in this kind of a plot, you see how the parameters, they migrate towards the final values. No, there is no rule of thumb, right? It is, at the end, it is always the matter of negotiations. All right. Is this clear? What I have just explained? Come on. Yes, yes, yes. Fine. Because now I'm going to run another example. Another simulation run, right? So basically, what we did controller tuning here, and then we stopped it. We moved the operating point, and then we would move the controller tuning here again, and so on and so on. The question now is, what happens if the controller tuning is turned on all the time, right? So the easiest thing would be just to turn on the controller tuning all the time and let the plant run, right? And then see what happens. Okay, if the controller tuning is running all the time, then the PRBS is injected all the time and so on and so on. But let's just assume that that's okay, that we have no problem with that. So what I would do now is I will run that again. Okay, is there something else I wanted to say before that? Yes, okay, the forgetting factor lambda, you see it is here and it's set to a 95. So if, now I figure, okay, let's take a look at here. Somewhere here, where was it that we identified the model? So we started to identify the model here again. Yeah. And no, here we already stopped it. Okay. No, why we identify it there? Yeah, here. You see, there were, no. It was definitely here. Okay, here. You see that here are the parameters which then somehow then converge to their here, you can see it here, to their kind of a final values, right? So now if lambda was set to a smaller value, definitely the parameters would converge faster, right? If it is a bigger value, it would converge slower, right? But then they would react to changes faster, which might bring the system to instability. This is about, we could do a few experiments with the different lambda, but it'll take too long, right? And at this point is not that important. Something else is more important that I want to show. So I will now run on a system again, the experiment again, and we will start with some low operating point like that, right? And I will, okay, so the control panel, the system is running. Okay, I'll need to turn the loop off and turn the algorithm on. Okay, so another thing before we go on. So you see, when the system is kind of identifying, so when the auto tuning is on, so you see the controller parameters here, they change constantly. You see, they're moving all the time. So now, what I'm going to do now, I'm going to actually do the automatic set point change. So I'm not going to do it manually, but I'm going to just run some pre-recorded test run like that. And I'm going to leave the identification or self-tuning on, right? So like that. Okay, no, I need to close the loop first. I hope it won't explode. No, it didn't. Like this. So you see now the P matrix it gets constantly updated all the time, right? And now what we did here, we did a relatively big set point change, and then went to the middle set point and to the low set point. And now we will gradually change the set point from the low operating region to the high operating region while the controller is updating all the time, right? And maybe, okay, maybe if I change the lambda now here a little bit less, so to like this, you would see that the parameter will converge faster, and we can see that the matrix gets black and white faster, like this. But I'm going to put it to 9.5 again. So like this, that's okay. And now I'm going to turn the set point change off again. And now I'm going to leave the adaptation on, and I'm going to manually change the set point now. So to some small value like that, or to even smaller value. And now I'm going to change it really, really fast to, for example, okay. Anyhow, so this is what I wanted to show. What I wanted to show, and I'm going to do the first things like that. Come on, will you be able to zoom it in properly? Probably not. Or maybe I do it like that. No. Give me 1 second. So this is the the outputs of output of 2. So 0 to 1 2000. Okay, so now it'll be easier to see. Now this is my, do you see the plot now?
Yes.
Okay, so now this is my closed loop response over the change of the operating region, right? When the adaptation is on all the time. And what we see that we never really get the response that we want, right? The response is never good because the adaptation is on all the time, right? And the system is changing all the time. And while it takes relatively long time for the system to get identified in order to tune the controller well, right? And then this works for a small set point changes, right? So when we change the system, so when we did the set point change even bigger, you see the response was even worse, right? For the big set point changes, when you do the adaptation, it takes quite long for the system to adapt, and in the transient region, right, we get a really bad response, right? For the small set point changes, as seen here, it is better, right, but still not good. See, because it takes quite a long time for a system to get to the steady state. And then when I wanted to do a really big set point change, right, the system went unstable immediately, so it blew up immediately, right? So the adaptive control is good, right, for the gradual, very slow set point changes. For the big set point changes, you see that it takes the adaptation takes too slow, right? And since the controller parameters are constantly updating, and if the system changes too fast, the adaptation doesn't really have time to react. So that's why it could be that it brings the system to the unstable region, which happened to me here. And this is what I said at the beginning, that it is very likely that something will go wrong with the simulation. And this I want you to remember. I mean, adaptive control is fine, and it is good, and it is a powerful tool, but you really have to be careful what you are doing. Is this clear? Look, I spent an hour, right, trying to explain this example, and this really is important thing for you to know, and ask me questions now if you do not understand, or just actually what I wanted to show here, it should be clear. Is this clear to you or not? And if you have questions, go ahead now. Okay, so let's now, so this is what I wanted to show you regarding the recursively squares algorithm and self-tuning controllers, adaptive control, whatever you want to name it, right? So this is how it works. Now, basically that's it. This is what I wanted to say about the linear systems. Just to make short and quick conclusions, right? So the dynamic system identification is a procedure when we deal with the linear, right, and close to linear systems, right, for the linear systems, I mean. The excitation is of the extreme importance, right? So the better excitation do you have, right, to excite the system and to collect data, the better chance you have to get the good model parameters. The structure selection, right, the choice of regressors and order selection, right, and the model validation is the key, is the essence, right? This is something that you really need to do carefully, especially the model validation, right? And of course, the model validation should be done on a different set of data. System identification is kind of a iterative procedure, right? So you trial and error, you try different things until you get kind of a model that you're happy with. So in general, it cannot be fully automatic, but for the linear systems, we can actually bring the entire procedure to the high level of the automatization. You need to remember that the result of the modeling is always a model. It is never a copy, right? It is a model. It is approximation. You will never have, let's say, the exact copy of the system. This is important to know. So the quality of the model depends on the entire process, starting with the design of experiments, data collection, filtering, and so on. The data kind of a pre-processing, then order selection, and whatever we were talking about, right? Then the executing the least squares or any other calculation techniques for the parameters. And the recursive least squares is a powerful algorithm, right? Which can be used for advanced control applications like self-tuning and adaptive control, but it has its own weaknesses, which I tried to demonstrate in the example. Here are some references, right? That if you want to actually explore the matter further, you are more than welcome to do that, right? I actually use this first book, right? Leonard's young book, and everything is in that book that you need to know. Okay, this is now to conclude the linear dynamic system identification. Go on with the questions. Questions?
In reality, when you really go to a company that has such a tank, as you showed us in the example,
Yeah.
then what would you really do? There would be a controller, but for example, the operator is not satisfied with this controller. That's why he's with you. And then you come and really build it as you showed in the example. So you bring in such the excitation signal, and do you really change the existing controller by a new computer, or how is it, or how can it be done?
Exactly as you just said, right? But this is far more difficult than you can even imagine. This is usually not a technical question, it's a strategic question, and usually it involves more, let's say, salespeople than the actual engineers, right? The tank that I have showed, it's actually the real system, and it is a widely used example for studying the nonlinear control techniques, right? So you Google CSTR, right, and you will find just about 2 million of examples. How is it done, right? this was, for this particular example, what I wanted to do, I wanted to show you how the adaptive control works, right? And then I also wanted to show you that that's not the end of the story. So that the adaptive control is very good. However, it has difficulties. How it's done in reality, it really depends what people really need and what they want, right? So if they operate, let's say, mostly on one single operating point, then let's say automatic self-tuning control is very good. You run it once, right? Maybe, and then it runs for a half of a year. And then when things change slowly, then you run it again and that's fine, right? But then the problem is, you see, with the reactor, I mean, according to my experience, right, the most difficulties they have, right? So this is the reactor. When kind of sometime when the ingredients, they change significantly, right? Sometimes the ingredients, they have a different temperatures, they get a new batch and they're different, right? And then this actually governs the change of the dynamic of the system, and then you need to retune the controller, right? And then if you have a good operator who knows how to tune the controller, let's say from experience, then you don't need automatic control, right? They will know and they will tune it, and then it is going to be okay, right? But most of them, they don't. Right? In reality, it really depends depends of the project, really, right? That's all. And what the difficulties usually are that people don't really know what they want. They don't know, and they don't know what can really be done, right? In this kind of a, let's say, there is an example that I like to tell in that kind of a, that it's a story really. Long time ago in 2000 and 2006, at AVL, I was working at that time at the different department that I'm working now. But we were asked to actually tune the torque controller for the engine testbed for a Ferrari. And yeah, we did it fine, and then it was okay. But there was a guy, I think it was 70 or even older, right, who actually just walked into the testbed room, right? He was not allowed, but he did it anyhow. He actually took a long screwdriver, he put it somewhere into the engine, and he was listening, right? He put the air onto the screwdriver and he was listening the engine, right? And based on that, he was able to tune controller better than everyone, right? But this guy had about 50 years of experience of doing that. Without that, right, it would be very hard. But then when this guy has gone, then nobody else was able to tune that controller on his way. And then all this, let's say, automatic tuning controller techniques came really handy. It really, as I said, it really depends of a project, really.
Okay,
Do you have more questions? I mean, look, those things are important. I mean, they really are, right? How do you come and how do you attack the problem? And most of the thing, I mean, it is really important, the design of experiments, as I said before, right? So what are you going to do? How much are you going to disturb the system in order to identify the model parameters? And once you have the model parameters, then you will be able to tune your controllers, right? The better the model, the better the controller. And then for what cost, what are you going to do, how much are you going to disturb the system, and if you're going to disturb it, how much is going to cost you. And the cheaper you can do it, the better it is, right? The more money you make. Is this clear? I mean, do any of you have any industrial experience with the control engineering or with the system identification or whatever? Or are you just straight from college? Anyone? Okay. All right. Any more questions regarding the linear systems? Linear system identification, or any questions regarding that, what we said up until now? Okay, so then we will continue with the nonlinear systems. So we have another 50 minutes, right? And today, now I am going to actually talk about the nonlinear systems and nonlinear dynamic. But first, I mean, really, what is the difference between a linear and nonlinear systems, right? We were talking about the nonlinear system, about the reactor before, when we've seen the very nonlinear differential equations. So can someone explain it to me, what is a linear system and what is a nonlinear system? What do you understand as a linear as opposed to nonlinear system? Or give me an example. Anyone?
As you said, if there are some exponential functions, then it's nonlinear. So you have the exponents.
Exponential functions where?
In the
model description.
system.
Yeah. Okay. But now let's just take a look at a general, right? What I really want you to understand what the linear system is and what the nonlinear system is. So if you have a sound system at home, right? A high quality sound system with the amplifier, right? So what happens is, if you have a knob on the amplifier which increases the volume and decreases the volume. So now if you turn the knob towards the right, the volume on your speakers is going to increase. And if you turn it even more, it is going to increase even more. If you turn it on the other way, right, counterclockwise, the volume is going to decrease. And if you're going to turn it even more, it's going to decrease even more. So this is a pure linear behavior, and this is what you want from your amplifier, so that it is linear. So that turning the volume, it is actually really turning the volume, right? And the other way around. If your amplifier would not be linear, would mean you would turn the knob, right, the clockwise, and the volume might not increase, right, or increase very little, or if the system is very nonlinear, it might even decrease. And if you turn it even more, right, it might then really suddenly increase a lot, right? And if you put it back, it would not do what you would expect. And that would be a nonlinear system, right? So this is the probably the simplest the simplest example I can come with, right? In reality, the linear systems, they kind of behave the way you would expect. And the nonlinear systems are every system that is not linear, right? So then you would expect kind of a difficult or strange behavior. You will see it in the later. Now, we have, when we talk about the nonlinear models, we talk about first about the static models, so that we have the input and output data, so the input-output map, right? And the relationship between input and output is nonlinear, so it's kind of a different, right? And that kind of a static models, they would be able to interpolate and extrapolate around the operating region. Then dynamic models, right? So then we can extend the static models on the dynamic models. And that it is usually done for in the nonlinear system identification or nonlinear modeling in the way that we have one step ahead prediction nonlinear map, right? And then by the choice of the regressors, so the choice of the input and predicted outputs, they're then delayed back, right? So the inputs, the number of inputs are delayed and they're fed into the nonlinear model, and the number of predicted outputs, they're then delayed as well and fed back to the model. And in this way, we actually create a dynamic structure of the model, right? How many delays, right? This is called the order. And which ones? So how many inputs and how many outputs are we going to take? This is then again the selection of the regressors. So this is yk hat, yk minus 1 and blah blah, right? uk minus 1, uk minus 2, those are the regressors, right? And the z minus 1s are delays, right? And how many regressors, how many delay blocks, this defines then the order of the model. Is this clear? Now, basically the neural networks, right? The neural network models, when we want to create the neural network, right? The training of the neural network is actually the nonlinear system identification. So getting the trained, for example, the neural network to behave as a dynamic nonlinear model, this is basically the nonlinear system identification task. Again, the important thing is, right, never estimate what you already know. Again, the same as with the linear systems, we have a white box models. So these are the physical model. So if you now remember the CSTR, the tank reactor, the two equations that I have showed you, right? That's a white box model. So a pure physical model, right? Gray box model is a kind of is a little bit of this and a little bit of that. So when we know something about the kind of physics behind it, and what we don't know, we model it with some sort of the maps or something similar, or some parameters and stuff like that. And then we have a black box models. These are the neural networks, fuzzy models, wavelet models, and so on and so on. Have you ever heard for the fuzzy models before? You know what a fuzzy model is? we will talk about that, not today, but probably tomorrow. Some vocabulary, right? About, I mean, this is just important for you to know that most of the things are the same, they're just called differently. So let's say to estimate the parameters, it also means to train the parameters. That's what the machine learning people would tell you, right? Identify means learn, validate means generalize, model structure, right? What we call the model structure, they would call it the neural network topology or architecture, right? So our estimation or identification data is a training set, right? Validation data is a generalization set. Overfit, what we call it overfit, they would call it overtraining. We call it output, they call it target, and so on and so on. So basically, it is important for you to know that there are many different words for the same things, right? Let's talk about the practical point of view, right? So the nonlinear system identification is really much more complex problem than the linear system identification. I mean, it really is. It's iterative process, right? And you never really know what's right and what's wrong, right? You don't know, you try, right? So the identification procedure in that way, it's almost never can be fully automated, right? If you want to do the nonlinear system identification, you must have some sort of the software. Forget about with the pen and the paper that you're going to do anything, that you're going to build any useful model without the computer. And as always, you need a good set of data. Right? Good set of data, good set of data, good set of data is very important. That's why everybody now is collecting data about the coronavirus. Everybody wants to get as much tests as possible in order to build their nonlinear dynamic model for a prediction of the next virus spread. Right? So it is very, very important to have a data, and that's why everybody wants to build some sort of applications which they're going to place in the mobile phones so that they can track people and collect data so that they are able to actually build the models. Data is very important. Data is very important. It is important to how to set up the experiments. Data is very important. Data is expensive. Data. Remember that. High quality data. In our case, the high quality data means the data which represent a dynamic of the system in the wide frequency range. Experience helps a lot, right? As I said before, the utilization of the simulation software is actually necessary. It is up to you which software are you going to use. I'm used to MATLAB, and I don't know, is this a bad choice, the best choice or not, but this is what I'm used to. Right, questions up to now? No.
What is an example of an alternative software? Can you name one? Or
Octave is one of them, right? So this is the kind of a free MATLAB. Then what they're using it. I just lost it. There are many alternative software packages for the system identification. So if you remember last time, I showed a little bit the the system identification toolbox. There are many toolboxes for MATLAB which are free as well, right? Google it, you will find it. You will find it. There's one. I can't remember right now. I'll think of it till tomorrow. There is one package, right, which boys really extensively use for machine learning and the training of the neural networks, which is good because it runs on the graphic cards, right? And the graphic cards, they have much faster processors because they're RISC processors. They are actually built to do the simple calculations, right, very fast. So the RISC processor is able to do the multiplication and summation in the one clock cycle, right? And this is very important. This is very useful in the linear algebra with the manipulation of the matrices, right? As soon as you have anything to do the model estimation with the data, with the neural networks and parameter estimation, you end up doing things with matrices. Inverting the matrices, if not the inverting the matrices, finding the inverse, which is kind of an inverse, right? Some sort of approximations, as we've seen with the recursive least squares, and doing so, the matrix manipulation is very important. And these tools, software tools, they operate on the graphic cards, right? Which they use the RISC processors, and that's why they're so, let's say, popular. Okay. Nonlinear system identification problem is to find the nonlinear mapping, to find the vector of regressors, right? And to vector of parameters, and to actually identify the parameters and get the correct nonlinear mapping. So that this is written like that. So if our nonlinear system is shown as so that the output is a nonlinear function of the inputs and outputs and some noise, right? So what we want to find the set of parameters and the function which will provide us the prediction. It is much easier said than done, right? But anyhow, now we looked at some common regressive selections, right? And the model structures in the linear systems. This is the slide from the last week. I don't know, I think exactly a week ago we did that, right? Where we looked of the RX input error box and Jenkins models, right? Where a particular structure is selected by the kind of using different type of polynomials. And this is true for the linear systems. For the nonlinear systems is exactly the same thing, except that instead of that in front of the particular model, we just put the letter N. So Rx for the nonlinear system is a nonlinear Rx, right? And output error for nonlinear system is a nonlinear output error, and so on and so on. Now, the prediction equation for the linear system was like we had the vector of the regressor vector multiplied by some vector of parameters. This represents the linear set of this represents a linear system. So the vector of regressors multiplied by the vector of parameters. For the nonlinear systems, we have some sort of a function, which is a nonlinear function. It's just not it's not only multiplication, but it is a nonlinear function of the regressors and the theta and the parameters. Is this clear? Or are you confused? Okay. Now, I'll go back a few slides. Just I want to make a point. This one. Number of the delayed. So do you understand this block diagram, this picture here? So nonlinear model, right? One step ahead predictor, nonlinear one step ahead predictor, and then a number of inputs and outputs, right? Fed back to provide the regressor vector, right? Now, the question is, how many inputs, how many delays do we need to select? So that means the question, one of the important questions here is selection of the order for the nonlinear system. Now, how did we select the order for the linear system? How did we select the order for the mass spring example that we did the last time? Come on, someone should tell me that now.
From the derivatives.
From derivatives, what did we do? We count.
We look how many times we derivative our system, and that's the order.
Okay, so what we did, we count the number of dots, correct?
Yes.
We count the number of dots, right? So the higher number of dots on let's say a derivative, right? That was our order, right? This is correct because we knew the order, right? What would we do if we didn't know what the order of the system is?
System identification toolbox.
System identification toolbox, or we would guess, or we would try, right? We would try, we would do first order, second order, third order, and then we will see which one would do the best, right? But anyhow, so if the order is known, right? So then it is quite easy. Our model should be the same order as our system, if we know that. Now, the nonlinear system here is much more complicated, right? And this is one of the biggest problem in the nonlinear system identification, to select the order, right? And basically you will always end up trying it. So how many inputs and outputs should we select? But in general, right, the Takens theorem kind of tells us how to select the order, right? The Takens theorem is named after the Floris Takens. So this is the Dutch mathematician. He was doing something completely different. He was studying the chaotic systems, so chaotic dynamic in the chaotic systems, so those strange attractors and stuff like that, right? But what he actually made, what he found out is that it is possible to reconstruct the unknown dynamic, right, by analyzing the time series of the data, right? So basically he sampled the data, right? So the input and outputs, and then he wanted to find out something, right, for his own research, but then he found out something which is very important for our order selection. So basically, for the linear systems, right, if we know the order, right, if we are able to count the dots, then we already know what order our model should be. But for the nonlinear system, right, this is not the case. So even if we know the order of the nonlinear system, right, if we are able to count the dots, right, then it is not necessary the number of the delayed blocks, so that it means that the order of our model should be the same as the order of the system. It should be somewhere between the actual order and the order which is twice as big plus 1. Right? So that means if we know the order of the nonlinear system, we have an idea that in the best case, really the best case, the order of the model should be the same as the order of the system. But in the worst case, the order should be more than twice as big, right? 2m plus 1. But in reality, it should be somewhere in between, where we don't know, right? And this is for the systems where we know the order. For the systems where we don't know the order, we have no clue, right? There is no reference, there is even no theoretical background, no theoretical reference how to select the order of the nonlinear model if the order of the nonlinear system that we want to model is not known. Okay. What should be your response here? What do you think about the statement that I just made? The moral of the story is it's very hard to know what the order of the model should be, right? And the Takens theorem provides us a rough kind of a reference how to select the order if the order of the modeled system is known. Otherwise, we don't know how to do it. So now, taking into account the Occam's razor, so this is the kind of a principle that the model should be as simple as possible, but not too simple, right? And the Takens theorem, right? This should kind of guide us how to select the order of the model, right? Is this clear? Right. So on the exam, when I'm going to ask you how to select the order of the nonlinear model, what are you going to tell me? What would be the right answer? The right answer would be hard, right? Okay, so we said that basically training or finding or getting the neural network, right, is the same, or the finding the correct neural network in order to be able to model some system is the same thing as a nonlinear system identification problem, right? So so nonlinear mapping is a selection of the nonlinear function, right? And basically this nonlinear function then can be decomposed in the way so that we have a nonlinear function, that we have a sum of some sort of a bias functions and nonlinear bias functions and the parameters. And this is exactly what we were looking at the very beginning at the radial basis function neural networks, where we had the basis functions, the Gaussian bells, and the parameters, right, they were weights. So how much these Gaussian bells were they kind of lifted up and down, right? And this is seen here. So this is a basis function, which depends on the input and output space, right, and the data and the weights. Now we can choose the Gaussian basis functions, so that means radial basis functions, RBF, right? we can choose different ones, and then the network would be called differently, right? For example, multi-layer perceptron. For example, in the fuzzy models, we would select the basis functions that would be just kind of some set of a partly linear functions, right? We will see that later, tomorrow, I guess. Okay. So when we select of basis functions, right, it is really, it depends of the application, what we want to do. Most of them, right, most of the common used basis functions, they are the universal approximators. So that means model utilizing these kind of a basis functions with enough of them and enough of parameters, right? With that kind of a model, we are able to model just about everything, right? But there are there's no exact criteria for selection of the functions, but for example, the practice has shown that if you choose the radial basis functions, is for the low, this is useful for a low number of regressors, right? So sigmoid functions, that means the multi-layer perceptron, they're better for the larger number of regressors. And the fuzzy models, they're useful when we can explain the behavior of the system with some sort of the linguistic rules, hot, cold, too high, too low, and stuff like that. We will see that later. Okay, is this clear? I guess it is. So now let's talk about the quality of the model, right? So when we use for the training of the model, when we use some sort of the cost, let's say mean squared error cost function, right? Then in this case, let's say the generalization can be done, right? So that means we can kind of expect some sort of a prediction error. So this prediction error is then the measure, right? How accurately a model is able to predict the output on previously unseen data, right? So that means we train the model on some set of data, but then we don't really get, we don't train it, but we kind of we don't test it, but then we kind of estimate what the cost function or what the error would be. And then this generalized error then can be decomposed to bias squared, to variance, and then some noise. Is this clear? Have you seen that before, what I'm talking about now? The generalized error, the expected prediction. Okay. Have you seen this graph before? This tells us the model complexity versus performance. So the more complex the model is, right? So more the structure is more complex, right? Then we are able, so the bias decreases. So we see that here, right? So the more complex model is, the bias gets smaller. And the less complex the model is, the bias is kind of a bigger. And when the model complexity is higher, then the variance kind of gets bigger, right? And these are not now these parts of the generalized error, right? Bias, variance, and this is called the bias-variance trade-off. So if our model, right, is not complex enough, right, then we get the model which is not able to fit the data properly, and this is called underfit. When we get really nice model, we get a kind of a model which is able to fit the data and yet do some sort of generalization. And when the model is too complex, right, we get the data overfitting, which means that the model wants to fit the prediction to each data point, and this is bad, right? So basically, what I wanted to say is, again, the model complexity should be selected in some right way. So in order to get the good trade-off between the bias and variance. So just a quick explanation, right? So the bias is really it tells us how well the model is able to predict the data, right? And the variance, it tells us the spread of the prediction, right? So how spread the data is. And this can be easily, and it is important to know, right, that there's always a noise which cannot be modeled, right? And the noise will always be present, and it can't be removed from our model, right? And then this bias variance trade-off, it is easy to it is probably the easiest to kind of explain with throwing the darts, right? So if when we have the high bias and the low variance, we would actually get the kind of a throws into the dart, something like that, so that they're very close together, but they're far off, right? So that means the model is wrong, but yet the kind of it is biased, right? When we have the high bias and the high variance, this is the worst thing that can happen, right? So the throws, they go everywhere, right? And they miss, right? They're off and they are everywhere. When we have a high variance and low bias, so that means we're actually throwing so around our prediction where it should be, right? And when we have a low variance and the low bias, this is what we want. We want to have the accurate model. And this basically, the bias variance trade-off is a kind of is an examination of the quality of the model, right? When we hit that sweet spot, right, with the lowest variance, right, and the bias, right, that's the model which is the best of all of them. Is this clear? Have you seen that before? Do you know what I'm talking about? Okay, I mean, I am telling you, this is something I'm going to ask you on an exam, probably everybody. Bias, variance, trade-off, Takens theorem, order selection. Make sure you understand that, okay? This really is important. Okay. Okay. How much time we have? Another 10 minutes. Okay. We have then basically, once we have the model, right, we do the validation, and the validation is very similar to as the validation with the linear systems, right? So when we have one step ahead prediction model, right, we take a look on the residuals and we do those, let's say, residual analysis, autocoloration plot, cross coloration plot, and see if the residuals are white. That means the model is okay, model is good, right? If the residuals are not right, so that means there is something left in the data which has not been modeled. So that means that the model structure is not, or the model complexity is not high enough. And of course, the parallel model is the one that really tells us how good the model is. Which this is how well the model is able to predict, right, the output based only on the given inputs, right? So that means the outputs for the outputs are delayed back, right? So the model is actually making a prediction based on its own prediction. Right, again, I mean, I could talk a lot about the nonlinear modeling, but the point is each, let's say, application requires its own kind of approach, right? So some general recommendation can be given here. So first of all, examine the data, right? Try to take a look, try to look at the data and try to see what is actually going on and try to find out the type of nonlinearity from the data. And sometimes it can be easily seen, right, from the input-output behavior, for example, that there is a quadratic relationship between the input and the output. This usually what happens when you try to model the power, right? Always try the simple things first, right? Try simple structures, right? Low model orders, a small number of parameters, and then see how that kind of a simple model is able to model the data, and then try to increase complexity if necessary, right? Always take into account bias-variance trade-off. Don't go and increase complexity too much, right? Take into account that the Occam's razor, so that the model should be as simple as possible, but not too simple, right? When you select the order, right, take into account the Takens theorem, look for the order that it is between the order of the system that you want to model and at least twice as big, +1, right, as the real order. If you don't know what the real order is, then trial and error. Try to take a look in a physical description and characterization if you can, right? This actually provides the useful information for the choice of the regressors and also the order, right? Always split the data into the estimation and validation data sets. Always. Filter the data, right? Do proper kind of a signal signal conditioning. So center the data properly, detrend, remove the offsets, right? And the scale data. So especially for the nonlinear systems, it is very important that the data are scaled. So that means that they are kind of either dynamic, it is in some sort of the same region, right? Sampling time, as we were discussing before, right? Sampling time should be sufficient, right, to capture all the important processes and dynamic. So if possible, try to find how fast the system is, and then so the fastest pole or the fastest frequency in the system, and then sample at least twice as fast as the fastest frequency. So you need to know what the input to the system is and what the output of the system is and what are the disturbances, right? And select the correct distribution of the inputs in order to excite all the frequencies of the output signal. Is this clear? Okay, just a very quick example, right? So this equation here is nonlinear, right? So it is definitely, it is a nonlinear system because we have a tanh and we have the input which is on a power of 3. So this is far away from being a linear, right? So you asked about a software, right? So this is the Toolbox nonlinear system identification, right? This Toolbox exists for the MATLAB and it's free, right? This Toolbox was used for this particular example. So the regressors were selected as an input as an output. So that means only so that the order is that the model is a first order, so that it's a static model, right? And the type multi-layer perceptron, right? Could be anything else, it's not necessary. And then basically after some playing with the system, right, it was found that one hidden layer with 5 neurons provide a good result, right? And the structure of the model is nonlinear RX model. So identification data were like that, so input and output. These are then validation data, so the data were split to 2 parts, and this is the real system, and the population of data across the input space and the output, right? So the output here is yk plus 1, and this is the approximation of the neural network, multi-layer perceptron approximation, right? And then validation model on the validation data set, we see that the model fits here perfectly, and this is the error, right, of the system. Now, if you take a look at the validation, right, to see that the model and that the model really fits the data well, right? So this is too good to be true. Why is it too good to be true? Why do we have such a good fit here?
Overfitting?
No,
there is no noise.
Exactly. There's no noise, right? So, I mean, this is just a stupid example, right? Because there is no noise, and you see that this is the artificially generated example, no noise. And once we have no noise, we can actually train the neural network really to fit the data properly, right? And this is never the case. Okay, so now this is actually, look, I spent, now we have 4 minutes left, right? I spent more than an hour in the CSTR example. And now this is all that I wanted to say in general about the nonlinear system identification, right? The point is, the nonlinear system identification, it is so complex that there's nothing really much to say about it except it's very hard. And then it gets very, very complicated when we take a look the stuff into the more detail, right? So in about 40 minutes, I was able to say everything what I wanted to say in general about the nonlinear system identification, right? From now on, we are going to take a look some particular points into the nonlinear modeling, right? And this is what we're going to do tomorrow and on Friday, right? And then next week, we're going to take another look on the nonlinear system identification. So what I wanted to do for today, but again, it's not enough time. I wanted to do further the example of the CSTR of the tank. And I'm going to stop here, right? And we're going to continue with that tomorrow. It's not going to take long, maybe 10 minutes, 5-10 minutes. Okay, now, at this point, I'm going to, it's the end for today, right? So I'm not going to do anymore. But in this 2 minutes, which is left, right now, we are about on the halfway, we're a little bit more than halfway through the course. So what do you think about this course what do you think about the lectures? I mean, how do you feel about it? What is your level of confusion, right? How much do you know about, how much do you know about the things from before? What is new to you? Are you afraid of it? Does it scare you? Are you happy with it? Give me some impression right now. Anyone?
For me, most of the things is new.
Okay, fine. And what do you think about it?
It's interesting, but for me it will be hard really to really tell you again what you told me. So I have to go through and through all the slides.
Okay, do that, right? And do that and ask me questions about it. I know, I am aware of it, that this is extremely hard thing to do, right? What I'm telling you in these lectures, right? It is something that I spent 20 years with. And I still get, I still get stuff that gets really kind of a surprising, right? So I am really aware of it, that the matter that I'm trying to explain it to you is far away from being trivial, right? But then again, you need to tell me what do you understand and what you don't understand and what is hard for you to understand. And you need to know that what I want that you get from this course is that you're able to do the engineering work when you go to work, right? Okay, boys and the girl, I have to go now. I have a meeting at 3 o'clock. Look, I thank you very much. We'll continue tomorrow.
Goodbye.
Bye-bye. Have a nice day. Talk to you tomorrow.
You as
Bye-bye.
well.